Hello, everyone. I'm Hui Bingqiu working at Nanchang University. I will report on the latest progress of our research group NCST team. The title of my presentation is Initial Analytical Theory of Plasma Disruption and Experimental Evidence. Next, I will make my presentation begin with background and motivation. Fusion energy provides by magnetic confinement tokamak reactors holds great promise, sustainability, and clean energy. Tokamak is a device that uses young magnetic fields to confine high temperature plasma with the aim of creating the condition for extracting energy from the fusion reactions that take place in the plasma. However, thermal and magnetic energy in the tokamak can drive plasma instability, leading to disruption, which is a core science and engineering challenge for nuclear fusion to actually generate electricity. Disruption abruptly disrupts the magnetic confinement of the plasma, termination the fusion reaction, and rapidly depositing plasma energy onto the confined vessel. The resulting thermal and electromagnetic force loads can cause irreparable damage to critical device component. The analytical theory of the tokamak plasma disruption is developed on the basis of the non-extensive geodesic acoustic mode theory, and is an analytical theory that can give the physical mechanism of the plasma disruption phenomenon. It can be used to guide avoiding the generation of plasma disruption, and at the same time, it provides more positive information for predicting the occurrence of disruptions and provides new ideas and new solutions for improving the accuracy of prediction. For example, as long as the ion extensive parameters are monitored and by drawing a warning line, the disruptions can be avoided. Then, combined with deep learning prediction algorithms, the occurrence of disruptions can be more accurately predict, accurately predicted. The theory of plasma disruption have been tentatively studied, but there is no analytical theory reliable enough to describe the disruption. Currently, there is only some progress in the prediction of disruption from the perspective of machine learning. However, the development of non-extensive geokinetic theory has brought an opportunity for the study of the analytical theory of the disruption. There are increasing evidences that non-extensive statistical mechanism can be considered as the basis for the more appropriate theoretical framework to describe complex systems whose properties can't be described by Boltzmann-Gibbs statistical mechanisms. Here we propose an analytical study of the plasma disruption based on non-extensive geokinetic theory and give the physical mechanism of tokamak plasma disruption, which is supported by the experimental data of 59152 shot on T10 device. We assume that the plasma can be described by non-extensive statistical mechanics, and based on this, we establish the non-extensive geodesic acoustic model theory, and then an in-depth analysis of this theory found that when the ion non-extensive parameter is in a specific interval, a strong wave particle resonance interaction will occur in the plasma, and the wave will continuously absorb energy from the plasma until the amplitude is too large and the plasma disrupts. Thus, a disruption event occurs. The test process of this tokamak plasma disruption mechanism is presented in Figure 1. This is Figure 1. Some schematic of test process for the tokamak plasma disruption mechanism. Physical mechanism of disruption and prediction. In order to investigate the physical mechanism of tokamak plasma disruption, we make an in-depth research on the theory of non-extensive geodesic acoustic mode, which is based on non-extensive geokinetic and obtain dispersion relation for the non-extensive quasi geodesic acoustic mode as follows. See the equation 1. The above formula is shown in three-dimensional picture. This is Figure 2. Multi-angle diagram from physical mechanism of tokamak plasma disruption. There are two peaks appearing at QFI equals 3/5 and QFI equals 1/3. In order to clearly illustrate the laws contained in equation 1, we use Figure 3 and Table 1 to clearly explain it as follows. This is Figure 3 and this is Table 1. The above theory is a natural conclusion of the non-extensive geodesic acoustic model theory based on non-extensive geokinetic, which guarantees the credibility of disruption physical mechanism proposed in this work, while demonstrating the potential of non-extensive geokinetic theory. According to the physical mechanism of disruption proposed above, we can give a testable prediction. When the tokamak plasma disruption occurs, the ionic tensile parameter measured by the method of ionic tensile parameter diagnosis will be very close to 3/5. This will provide us with important methods and ideas for avoiding disruptions and enhances our ability to the prediction of disruption. Evidence for the prediction. To confirm our prediction about the ionic tensile parameter measured by method of ionic tensile parameter diagnosis is very close to 3/5 for disruption. We tested its use 59152 short experimental data on T10 device. Test of prediction by disruption experimental data on T10 device. Figure 4 verifies that the prediction is correct. This proves that the proposed physical mechanism of disruption is also correct. It's indeed that disruption will occur when the imaginary part appears, because with the measured interpretation of phenomena allowed disruption. We proposed the physical mechanism for disruption and proposed verifiable prediction at the disruption of plasma in tokamak. The ionic tensile parameter measured by method of ionic tensile parameter diagnosis will be very close to 3/5. Then the prediction is confirmed by the 59152 short experimental data on T10 device, which proves the credibility of the proposed physical mechanism for plasma disruptions in tokamak. At the same time, the proposed theory can reasonably explain the phenomenon allowed the plasma disruption, which makes the proposed theory more credible. Our research results has clarified the physical mechanism of tokamak plasma disruption, which is the key to solving the problem of disruption on future fusion devices such as ITER. This is some reference. Thank you for your attention. That's all. Thank you.